In this video, we're going to be thinking a little bit about valence bond theory. So you've used this before in, for example, Orgo, when you talked about how carbon would make bonds to other elements. But we're going to see it from a slightly different perspective this time and apply some of our new understandings of quantum mechanics to help tell us how bonds really work under the assumptions of valence bond theory. In this, we're only going to be talking about diatomics. Later on in the semester, we'll talk about polyatomics and see how they're similar, how they're different. So when we're thinking about covalent bonds in general, really what this is, we recognize, for example, when we dealt with Orgo, we would have hydrogen, it wants to interact. Each one of them has an electron, so we share between those, and that's how we thought about valence bond theory for Orgo. But now we start recognizing it's not quite as simplistic as that. And really what covalence bonds are is they are an overlap of the atomic wave functions that we've been talking about. So for example, let's look now here. We have our hydrogen example using our orbitals. So hydrogen just has a 1s orbital, so it's that nice spherical shape here, and it has one electron. Here we bring in another hydrogen with its one electron, also looking like a sphere. But now what we need to recognize is that sphere of electrons is described by our wave function for that hydrogen atomic orbital on A and the wave function which is on hydrogen B here. So when we're actually forming these interactions, forming a bond, there's two ways we can do this. We can either look where we are going to be subtracting the two functions, where we are going to be putting now the wave function so they overlap with the electrons both spin paired, which probably we recognize isn't the most thoughtful. We normally don't think about spin paired in that way. Or we can think about the sum of the two wave functions, which is where we are adding those two orbitals with our spins paired so that one is up and one is down. We should probably recognize that one of these is going to be lower in energy, so that is over here, whereas the other is going to be higher in energy. Because now we're trying to pair spins that have the same upward spin. That's a higher energy state. So this is how we actually form bonds in valence bond theory using what we understand in quantum mechanics. What we call this is LCAO, which is just an acronym for linear combination of atomic orbitals. Linear being, hey, we can either do a subtraction, we can do an addition. Those are the two linear combinations that we can make of this. And the one that we normally think about being the most useful to us for forming an H2 molecule is this one over here, where we have the spins that are paired in such a way that one is up and one is down. One of the easiest ways to compare these two linear combinations, the plus versus the minus, is to plot the energy of this pairing as a function of the internuclear distance. So up here on the top in blue, we're looking at the energy as a function of the radius when we're doing this subtractive combination. Whereas down below here, we are looking at the additive combination, but we're still looking at the energy with respect to distance. And here we should see some very interesting features. So for example, let's first note over here on the left-hand side where our zero energy is. This tells us where our region of stability is. Negative is going to be the stable region. Positive is going to be an unstable region. So let's look what we have here at a distance of separation of about this is, I think, in picometers, so that would be 0.74 angstroms. We see the lowest energy, and we see an observed bonding for H2. So they're close together, and that is the lowest energy state, again, when we're looking at this additive version of linear combinations. If we look at the subtractive version up here, notice that it is always in the positive side. It never drops below zero. It never actually forms a bond. Therefore, we would say that this linear combination is a repulsive state. In other words, if we try to populate that, it will never be stable. So the only way we can form a stable combination for hydrogen is if we add these two together. That's where we see that a bond actually forms. Now, another way we could think about this is also we could think about physically transferring the electron from one hydrogen to another. And there's two different ways that we could make this combination. But it's still the same idea. We're still thinking about the wave functions, but now we're moving one wave function from one atom to the other. So we're going to call this something different. We're going to call this the wave function for the ionic species, which probably feels really strange when we're thinking about hydrogen. Hydrogen in a molecular state is not ionic in our normal mind, but we could technically describe it this way. It still shows the same principal aspects. So we would have a wave function that is part of that to describe hydrogen. So when we think about a molecule overall, we recognize that all three of these components, whether we have an ionic state or we have a covalent state, those are all possible interpretations according to quantum mechanics. So how do we deal with this overall? Again, we do that linear combination where we say, hey, the total wave function for our diatomic species is some combination of the covalent wave function times the ionic wave function. Also note that I have these C1 and C2. These are just coefficients for scaling. So in other words, in a case like hydrogen, we know that the ionic species characteristics are very low, so C2 is going to be essentially 0, where C1 is essentially going to be 1. That way we recognize that it's mostly covalent character for our hydrogen and very little ionic. So that's how we'll do this. And this is how we can describe valence bond theory from the lens of quantum mechanics. Admittedly, this is super clunky. It's really ugly from my perspective. So eventually we're going to have to move away from this and see something that actually is a little bit more representative of reality here. But like all theories that we use, it does have its uses. So for example, we can think about how do we actually form bonds? Well, it's when we have this overlap of our electronic wave functions. We might have described this earlier as the overlap of the electron clouds. So here I've got, for example, the hydrogen to hydrogen, the 1s to the 1s. But there are other ways that we could do this as well. So we could see the same type of interactions if we involve an s with a properly oriented p orbital, so that we see that the positive values of the p wave function overlap with the positive values on the s wave function. We could also form a bond in between our atoms if we have an overlap between two p orbitals. So we'd have, for example, here we might have the negative value overlapping with the negative of that wave function. Now, when we do this and we have an overlap along the internuclear axis, so between those two atoms, this is what we think of as a sigma bond, that single bond that we've seen oh so characteristically in orgo. Also in orgo, we saw other types of bonding. So for example, if I have a P and another P, they don't have to necessarily overlap in between our two nucleus here. So remember, here we're in the nodal plane right now, the way we're looking at those p orbitals, but we do see the overlap occurring here. That color doesn't show up as well in the red, sorry about that. And below, down here. So we see an overlap of those wave functions outside of the internuclear axis. And we have referred to these previously as thinking of pi bonds. So again, these are the same things we've seen before in other classes. Now we're just adding in the quantum mechanics part to it, where now we recognize these aren't just necessarily electron clouds, these are our wave functions. And valence bond theory can be actually quite useful and very simple to actually see how a bond can form between two atoms. For example, let's use the example of fluorine, which is a diatomic, and we look at its electron configuration. Here I'm highlighting our valence electrons because those are the ones that are involved with bonding. Those are the ones we're going to be interested in making the bonds. Here I've outlined the orbital diagram for these valence electrons. And really quickly what we notice here is, hey, thinking about our old perspectives of bonding, there's an electron here, there's an electron here. We can share between the two. Therefore, we could have that interaction. We just have to flip a spin there, no problem. And we could form an interaction between our two fluorine atoms. So yeah, we can make a bond here, and it is a single bond that we're easily to see where we can share those electrons. But really, this is a terrible explanation for the bonding in fluorine. If we were to look at the actual properties of F2, the 2p electrons are not the best way to think about this. But we're going to see more of that a little bit later. Despite it not being the best way of doing it, we could also use and have used valence bond theory to describe polyatomics. So for example, if we want to make a compound of NH3, we just recognize, hey, there's hydrogen, there is nitrogen that we're going to use to it. Well, hydrogen has one lone electron, nitrogen has 5, so it wants 3 electrons to form some sort of complex. So we could start thinking about the sharing of these electrons in this way. And that's all valence bond theory is. And we'll definitely see more on polyatomics later, but we'll see that it's going to get excessively complicated really quick. But for right now, it's a reasonable, simple model for us to use. Let's actually look where we have a little bit more of a problem here. So let's look at O2, diatomic. Again, I'm showing the electron configuration, 2s, 2p2, so nothing crazy there. But let's see what happens when we start bringing out the orbital diagram. Again, at first glance, this doesn't seem too bad because as I look here, I say, oh, okay, I need to share some electrons. Well, here's a pair that I can share. And if I get creative with my lines here, here's a second. And we say, oh yeah, we recognize that O2 has a double bond. And there we go. I've got my 2 pairs of electrons. So yeah, I could form a double bond with this. So in principle, it works, but there's a problem. Specifically, we're using the 2 p orbitals to make the bonds. So let's think about that for a moment. We saw earlier, we could, in fact, have overlap between the orbitals of p in such a way that we could form a single bond. That's nice. But then we have to say that's the only one that is in that internuclear axis. How do we know it's not, for example, using the out of plane? So it could also be said that for O2, it's not forming a sigma bond and a pi bond, it's forming 2 pi bonds. That's a legitimate explanation. But we recognize that's not the truth. We say O2 has a sigma and a pi, but this does not preclude that opportunity. So we're going to have to need to work with this and say, hey, how can we come up with a better theory that will more correctly show how this actually works out? Other problem that we'll see here is O2 is actually paramagnetic. And if we remember, that tells us that we are dealing with something that has lone electrons that are spin unpaired. But if we made our bonds, again, let me draw those here and here, then everything's spin paired. Where's the paramagnetism come from? So there are some quirks here with valence bond theory. It doesn't always work to show all the properties. So eventually we're going to need a new theory to discuss that. We'll do a couple more examples in another video of valence bond theory, but this one's already getting a little long. Sorry about that. But that's what I think we need to know for the intro here for valence bond theory. So as always, let's talk about this in class. Let me know what you understand. Let me know what's making you confused, and we can go from there. So until I see you next time, stay excellent to each other.